So this is 1.2 notes, and on 1.2 we're going to focus on linear equations using one variable. These are just equations where you have an x or a y, just one variable. There are no exponents. It's just simple addition, subtraction, and multiplication and division. And we want to be able to solve these. And so when we look for solutions to these, we're talking about any value for x where this comes out to be a true statement. Now, linear equations have lots of forms and lots of information about them. For instance, a slope for a linear equation is the rate at which things change. Now, we're going to be working with a one variable equation today, so there really isn't a slope to this problem. Slope always occurs when you have y's and x's. So this is really not part of what we're focused on today, but it's part of our description here. We also have what's called standard form. Again, this is an x and a y. You have slope-intercept form and point-slope form. They're all different versions of equations. What's important for us to note today is that when we talk about these linear equations, we're talking about things that do not involve exponents and things that can be solved using simple math. PEMDAS, exponents are not part of it, but multiply, divide, add, subtract are the steps we're going to go through for solving these today. And so some of the equations, are going to look very messy to start out, but this is not that hard to solve. We just need to go through the steps of simplifying and then the steps of solving. So the first thing I might want to do is distribute to get 2x minus 6. There's still a minus 17 equals 13. And this is a negative 3, so it's minus 3x and minus 6. Now, at this point, we need to simplify. I'm just going to combine everything that's on the left and everything that's on the right to simplify. 2x can't combine, but I get a minus 23. The 6 and 17 give us a negative 23. Over here, I've got negative 3x, and then a 13 and a negative 6 is a positive 7. Just looking at this, I like to have a positive x. It doesn't matter, but I like to. So I'm going to move the 3x over to with the 2x. Because that'll allow me to have a positive 5x. I'll take care of that. But while I'm doing that, I'm also going to add 23. I really want x alone, so I need to move the 23 to the other side of the equal sign. So 5x now equals 30, and I'm going to divide by 5. And x turns out to be 6. Okay, so valid answer, we like that. We could check it by plugging this in. 2 times 6, if I put a 6 there, that's 6 minus 3 is 3. 2 times 3 is 6 minus 17. That's negative 11. Over here, if I put a 6 here, 6 plus 2 is 8. 8 times 3 is 24. That'd be 13 minus 24, which turns out to be negative 11 as well. And so these do work themselves out. If we continue on just one more, we're going to check this one as well. 4 times 2x is 8x, plus 1 times 4 is 4, minus 29 equals 6x and minus 15. We're going to combine our x's by moving the 6x this way. And I really should simplify this first. This is a negative 25. So I'm going to add 25 to cancel it on both sides. Sorry, I probably should have done the 4 minus 29 first, but it comes out to negative 25, so I'm going to add 25 to both sides. Over here I get 2x, that all canceled, equals that canceled, and negative 15 plus 25 is 10. We divide by 2 to get x equals 5, and there's our second answer. Now, sometimes we get these linear equations and there's fractions, and so we want to be able to solve these equations in spite of the fractions. It's very simple. What we're going to do is similar to what we did in Chapter P. We're going to multiply everything by the LCD. Okay, and that's the key. When we do that, everything will cancel. All the fractions will cancel. So if I look at the 4, the 3, and the 6, the LCD in this problem would be 12. 4 goes into 12, 3 goes into 12, and 6 goes into 12. So now what I want to do is I want to multiply everything by 12, specifically 12 over 1. If I do it on the left side of the equal sign and on the right side, it should be balanced. And so I get 12x over 4 equals 24x over 3 plus 5 times 12 is 60 over 6. Now in doing this, I should now be able to reduce all these fractions. 12 over 4 turns out to make this 3x equals 24 over 3 is 8x plus 10. Excuse me. I want my x's together, so I'll minus 8x minus 8x to get negative 5x equals 10, and I'm going to divide by negative 5 to get x equals negative 2. And there's my final answer. Now, the second type of equation that's a fraction is when the x's appear in the denominator. There is one issue, okay? We're going to use the same rules that we've used to this point, but later we have to remember that the domains we dealt with before said there were values that were unacceptable. Anything that would make the denominator 0, the domain cannot be 0. So if I get a value like 0 here, 3 times 0 is 0. If I got a 0 for my x, I would have to reject that. So we have to start checking. As soon as you see x in the denominator of a fraction, you need to watch out. So first thing I want to do is I want to find the LCD of the fractions. Just think about the numbers first. 3, 18, and 2. Well, 3 and 2 both go into 18, so 18 is the numeric value. Then I have to think, okay, what do I need in terms of the variable? I'm going to need an x. One of the big questions here is, does 18x divide by each of these denominators? Would it divide by 2x? Yes. It'd be 9. Would it divide by 18? Yes, it'd be x. Would it divide by 3x? Yes, it would be 6. The second thing I want to do right now is I want to change this plus and make it a negative 1. The reason why is oftentimes we forget to deal with that. I always want to deal with those negatives between fractions early in the problem. All I have to do now is multiply by 18x the whole way through the question. 18 times 5 is going to be 90x over 2x equals 18 times 17. Wow, I might be really miserable here. So instead what I'm going to do is I'm going to write 18x, and I'm just going to cancel the 18 right away to say that that will be 17x. Now I could do the same thing here. The x's cancel. The 90 divided by 2 is actually just 45. Plus negative 18x over 3x. So that's what we get by the multiplication. But here the x's cancel, and the 18 divides by 3 to make negative 6. So the actual simplified version right now is 45 equals 17x minus 6. All I have to do is add 6 to get that 51 equals 17x, and if I divide by 17, x turns out to be 3. Now the question is, would 3 in either of these denominators make the denominator 0? Well, 2 times 3 is 6, that's fine. 3 times 3 is 9, that's fine. So I shouldn't have any problems here. But those are things to be aware of. You need to be careful to make sure you don't walk into a trap. So we look at another example. This one looks even worse, specifically because it's not x, it's not 18. The LCD here looks a little tough, but it's actually not so bad. Please remember that x minus 3 is a single item. Now these two fractions have the same denominator. That's really convenient. And the 9, it has a denominator of 1. So really the LCD is just x minus 3, because these two already have it, and this just needs it. So all I would have to do is multiply everything by x minus 3. You might say, how do I do that, Mr. Welch? Well, I would get x times x minus 3, that's bringing this guy in, but it was already over x minus 3 equals, and right now I know those are going to cancel, leaving me with just x. Over here I'm going to get 3 times x minus 3, that's the second distribution, but it's over x minus 3, and those will cancel, leaving me with just 3. Plus, now the 9, you know, I'm going to have to distribute this. Oh, whoops, plus 9 times x minus 3. Now there's nothing to cancel, so it's 9x minus 27. Well, I think what I'm going to do is I'm just going to move the 9x over, and I'm going to combine my like terms. This is a negative 8x. Now, this is where a lot of people get into trouble. They see the 3, the negative 27, and because I just moved across an equal sign, they think that they have to change the 3 or the 27. But what you remember is these are on the same side of the equal sign, so you just combine them the way they are. 3 and a negative 27 is negative 24. Now if I divide by negative 8, x will equal 3. But we have to go back to the original problem. If I put 3 in for x here or here, I get 3 minus 3, which is 0. I am not allowed to have 0 in the denominator. And so I have to reject this answer. And because I rejected this answer and there was nothing left, I have to say that there is no solution. All right, so we move on. We're going to look at this next piece. And it really has to do with the fact that sometimes, how do our answers come out? In other words, hey, I just got a no solution. Why did I get that? Is there any other way to get a no solution? Is that always the way it'll work? There are 3 types of solutions that you can get. In this first equation, if I minus x and minus x, the x's cancel. And what I am left with is 3 equals, what's 2 plus 1? It's equal to 3. Well, of course 3 equals 3. We've known that for years. There's no variables left, and I'm left with a true statement. This is called an identity, or something where there are infinitely many solutions. If I put 4 in for x, 4 plus 3 is 7. 4 plus 2 is 6, plus 1 is 7. It doesn't matter what I plug in for x, this is going to work. So every solution is really going to work for x. All real numbers. You might say all real numbers. Then number 2, sometimes you end up with an answer that is anything works as long as x is, and so in this case we'd add 5 plus 5. 3x equals 21. We divide by 3. Sure enough, x equals 7. This is a conditional. The answer is true if and only if x is 7. If x is not 7, this equation falls apart. That's the most common type of answer. The third type that's not as common is when there's no solution. The way we would get something like that is by subtracting x from both sides and getting 0 equals 4. Is 0 really equal to 4? The answer to that should be no way. This is not possible. It's a false statement. There's no x. So we call this no solution, or we say it's the empty set. You can just like that. That's essentially the same thing as saying there's no solution. Well, that's our work for today, and hopefully that's enough to kind of get you going in your assignment. Answer any questions if you have them. Good luck, and we'll see you in class.